All right, so this is Physics 1B for... This is the third hour of Physics 1B for November 9th. We are going to be talking now about refrigerators. A refrigerator is basically, it's a heat engine operating in reverse. It's often the way this is referred to. And this is a schematic of what the refrigerator is going to do. So the idea is that instead of taking hot energy and letting it do work for you, you're going to take... so this represents the inside of the refrigerator, which is at a cold temperature. And the idea is that you want to basically force the cold air... Well, that's the wrong way to put it. You basically want to force heat to transfer from a cold body to a hot body. Naturally, heat will always flow from a hot substance to a cold substance. So in order to make heat flow from a cold substance to a hot substance in the opposite direction, you need to supply work in order to make that happen. Okay? So in this case, what happens, if you think about what was happening with the heat engine, QC was always negative and QH was always positive. This is going to be the opposite because the QC is entering the system, right? So now QC is going to be a negative number, not a positive number. Oops. QC is coming in. So QC is going to be a positive number. QH is going to be a negative number because it's going out. And then the work will be positive. We can use the same equation we had before, which says that the work that needs to be put into the system to make this process occur is going to be equal to QH plus QC. Or because the QH is actually going to be a negative quantity, this would be the same thing as saying the absolute value of QC minus QH. And then we can isolate QH here to say that it's equal to QC plus W. Wait, that looks wrong. Did I write this wrong? QH is less than 0. Oh, the work is also negative because the work is coming into the system instead of going out. That's the biggest thing here. So the work is also negative. I'm just going to write what I wrote down in my notes here, and you guys can tell me if it makes any sense to you or not. The next line that I wrote was QH is equal to QC plus W. Maybe I should have put an absolute... okay, let's just think about this. I think there's supposed to be an absolute value sign here. Yeah, this doesn't follow from this line, but everyone agrees with that, right? There's some problems there. You all agree? Yeah, okay. I think I just need to put an absolute value sign on the W and it'll fix it. Would that fix it, do you think, if I put an absolute value sign on the W? I'm also just going to go real quick and pull to the book just to make sure. I left out a line here. So what they write is, they basically wrote this equation, and they rewrote it to say negative QH equals QC minus W. That follows from this equation. So let's get rid of this guy. I put that one in a little prematurely. These two equations are the same thing, right? Yeah. This equation follows from this equation. And then, if you take the absolute values of everything, you get this equation. So then this should be... Yeah, that's the part I knew. I knew that to be it. Yeah, so this is the absolute value of W. Okay. So there we go. Okay. So... the most economical type of a refrigerator is going to remove the greatest heat with the least amount of work in the process. So ideally, you'd want QH and QC to be effectively close to each other because then basically if you input... So this is exactly the opposite of a heat engine, right? A heat engine, your goal is to get as much work out as you possibly can. a refrigerator, your goal is to cool it off in the most efficient way possible, which means you want the energy that's expelled to be very approximately close to this, which would mean the work that you'd have to put in would be 0. Right? Does that make sense? So the most economical version of one of these, the one that was the most efficient for the money that you have to put in, because after all, you pay for the work, right? You're paying for the work because you have to plug it in the wall. So you'd want the most economical one would be with the work approximately equal to 0. So instead of defining the efficiency, and this of course is impossible. It's impossible to have a refrigerator that takes energy and moves it from cold to hot, basically cooling things off without the input of work. You have to input work to make this happen. Is it though? Sorry, wait. Okay, maybe what I'm saying is confusing, Daniel. What am I saying? What am I saying that was confusing, Daniel? Or are you just joking? I'm not sure. You said, is it though? You're referring to the statement that it's impossible to... Yeah, sure, okay. So here's the problem. Take a soda, right? That's a warm soda, right? And your goal is to cool the soda down, right? Now, you obviously know you can put it into a working refrigerator. It will cool the soda down, right? Or you can put it into a bath of ice, and that will also cool it down. That's a different process there, right? If you put a hot soda into a cold cooler, the cooler is obviously going to cool it down, right? A refrigerator is doing something completely different from what the cooler is doing, though, right? The refrigerator is going to use electricity to cool your Coke down, and the way it's going to do so, the only way you can do that, is to just push hot air out of the system. Does that make sense? In principle, when you have an unplugged refrigerator, right, that the only thing it has going for it is that it's insulated when it's closed. If you have an unplugged refrigerator, the inside is hot, right? So how do you cool down the refrigerator, the air within the refrigerator, which will then cool down your substances? The only way to make that happen is to expel heat, right? You need to get heat to leave the refrigerator. Does that make sense, Daniel? You need to get heat to leave the refrigerator. Now, will that happen naturally? Absolutely not. There's no way that will happen naturally. If it's warm in your house and it's warm in your refrigerator and they're at the same temperature, there's no natural way in which heat will just suddenly leave the refrigerator on its own. That will not happen. So you need to do work to make that happen. You need to basically pump heat out of the system. Yeah? And down here is a kind of picture of how that's going to occur. But that's basically the idea. The real answer is to make people like hot soda. Yeah. But then how are you going to keep your pizza good? You're going to leave it out all night? I don't know. So anyway, the most economical way to do this would have the work be approximately 0, or to have it be minimized, right? So instead of defining an efficiency for one of these engines, we're going to define something that's called the coefficient of performance. Coefficient of... Is it performance? Yeah. Performance. And what this is going to be is it's going to be related to the amount of... It's going to be the ratio of these two here. So it's going to be the Q cold that comes out divided by the work that's necessary to do that. Or written in a different way, this is going to be QC divided by QH minus QC from that equation right there. Okay, so this is going to be what's called the coefficient of performance. It has the symbol K. Your book makes the comment that it's usually on the order of 3. All right. And your book also goes through some calculations with regards to this to show that it's equal to something else. Let's talk about just how it operates first, and we'll come back to talking about what this number might be and how you can calculate it via other means. So there's a lot of stuff on this picture here, but we're going to try to go through as much of it as we can. 2 different types of refrigerator. Actually, it's the same refrigerator, it's just different schematic pictures of it. Okay, so we start at 1. You have a compressor. Notice that this is the refrigerator. This is the inside of the refrigerator right here, and these are the coils. Which, if you go look at your refrigerator after today's lecture, you'll definitely see these coils on the back of it, most likely. All right, so the compressor takes in refrigerant fluid. Okay, so I believe this is a closed system, right? Oh, maybe it's not closed. No, it is closed. It's a closed system. So you have the refrigerant fluid. That's your working substance. So the compressor takes in refrigerant fluid. It does work on the fluid to compress it adiabatically, and it delivers the fluid to the condenser coil. So the condenser coil is right here. So you start off by taking air from the refrigerator. It goes into the compressor, and then the compressor takes the fluid and does work on it to compress it adiabatically. So you compress it right here, and then it delivers the fluid right here. So that in that process, it looks like the temperature of the fluid increases. Am I reading that right? The temperature of the fluid comes from cold to hot. Yeah, so the temperature increases. And now you've got hot fluid, right? Now before the hot fluid comes back into your refrigerator, you want to make sure it's cold again, right? So you take your fluid. You have these lines right here that represent the fact that on the back of the refrigerator, these things are exposed to the air, and they're wrapped around like this to, I believe, expel as much heat to the air as you possibly can. So the fluid then condenses. It says compressed fluid in the condenser is at a higher temperature than the outside air, so the fluid gives off heat QH to the air, and the fluid partially condenses to a liquid. So I'm assuming this fluid can basically be a gas or a liquid within the regime of this, but the main thing is that the fact that this thing is hot, and I think if you go look at the back of your refrigerator and touch it, I think you'll notice these coils are hot, means that it's hotter than the outside air, so it can basically expel its heat to that air, right? Because it's hot. So if the temperature of the coils is like 100 degrees Celsius, let's say, that's kind of ridiculous, but whatever, and the outside air is at 37 degrees Celsius, then it's going to be very easy for the, those numbers are just insane. But the point is that as long as this is hotter than the outside air, then the air will cool it down naturally, right? Right. Okay, so then it says from there it goes into this expansion valve. So the fluid expands adiabatically through the expansion valve here. If the fluid expands, then it's going to cool down, especially if it's adiabatic, right? Because no heat's entering the fluid, it's just expanding, so it should cool down. Which means that the biggest thing is this. These colors are kind of maybe misrepresented. The biggest thing is that whatever the temperature, I'll do it from here. Whatever the temperature of the fluid is here, when it finally goes back into the refrigerator on this side here, it's cooler, right? That's the main thing. Is that it was hot over here, but it's exposed to the outside air. And why is it hot? It's hot because you basically took cold air and you compressed it. It became hot. You expose it to the air, which is cooler than it. It then cools down and condenses, and then by the time it re-enters the refrigerator, it's at a lower temperature than it was when it left here. Does that make sense? That's ultimately what's happening. You have fluid that comes out here, you compress it so it gets really hot, and when it's hot, it can expel its heat, and then when it comes back into the fridge, the fluid's cold. That's really all that's happening here. It's like the fluid, and then obviously when the fluid comes into the refrigerator, it's now colder, but this fluid is now going to give off its heat to the things inside of the refrigerator. Put it another way, that's the wrong way to put it. This cold air, this cold fluid that comes into the refrigerator itself is going to absorb heat from the things inside. So your soda cans and stuff that were hot are now going to basically heat this liquid up so that it's a little bit warmer here, and when it leaves here, and then it gets compressed and you repeat it again. So every time the cycle occurs, you're just expelling heat. I think of this as you're just pushing heat out of the system, right? You're basically just dumping heat out of your system. It's the same way that an air conditioner works, basically, right? And then, here's a kind of picture of what it actually looks like. So that's a refrigerator. Okay. We'll do some calculations here, but your book asks a pretty good question. And maybe you all already know the answer to this question, but do you think that, based on your knowledge of how this thing is working, or my confusing explanation of it, do you think that you can cool your house by leaving your refrigerator open?
No.
Why not?
Because, the heat just goes out of the refrigerator into the house.
Yeah, exactly. So technically, a refrigerator does what to your house? It heats it up, right? So the temperature in your house is going up, but the temperature in the refrigerator is going down by default, right? So yeah. Okay, so there we go. An air conditioner is the same thing, except you just make it so that the hot air leaves your house, right? So take the same concept, but basically expose the expose the hot coils to the outside air, right? And you get the same. This is kind of the same thing. There's another picture of it. You can look at that. Yeah. The back of the refrigerator warms the air up outside. That's exactly right, Kenny. That's exactly right. Okay, let's say one more thing about and a heat pump is another version of this where you basically flip it around. A heat pump, basically you try to heat a building by using a refrigerator in reverse, basically. That's called a heat pump, if you see that language up. So in terms of this quantity right here, let's recopy it down here. One that's not being very nice right now. So the book kind of mentions the following. You can think about what this performance coefficient is in the following sense. So if there's a heat current H that flows, and the heat current is related to the heat that's kind of going out of your refrigerator. So if H is heat current, this is a concept we learned about probably back in chapter 17, I think. Then the flow of heat in your system is going to be related to the rate at which the cold temperature comes in, right? So the cold temperature is coming in here, and the rate at which the cold flows out. I'm using the wrong word for this. QC is heat, right? The rate at which the heat flows out of the refrigerator will be related to this quantity right here. And then the rate at which work is done on the system is going to be related to power. Power is equal to the work done by your compressor divided by the time. Then we can rewrite this K here in the following sense. QC would be equal to H times T, and the work done would be the power of your compressor, which would be equal to, the work would be equal to power times time. So this would be equal to kind of the heat current divided by the power. That would also give you a way to describe what the performance coefficient is. And this is relevant because these other two quantities here are kind of more what we care about. It's the rate at which it occurs that really matters, right? So for example, for a typical, this is according to your textbooks, we have to kind of take this with a grain of salt. For a typical air conditioning unit, let's say this is like a window unit or something like that, the heat current is equal to about 1,500 to about 3,000 watts. This would be the rate at which you can actually push heat out of the system. And then the required power that you need for this, I'll write power here, is equal to about 600 to 1,200 watts. I have an AC unit here. I wonder if it says on it the actual rating for that is. I'll look later. I don't know. But to get these type of heat flows, the rating of this would be about 600 to 1,200 watts. So if we take a ratio of any of these, then K is going to be equal to about, if you do H over P, right? So 1,500 watts divided by 600 watts, then your performance ratio would be, what, 15 over 6, which is a little less than 3. What is it, 2.5? However, this thing right here depends on the external temperature. So, as an example, imagine the difference between trying to cool your house on a day when it's like 80 degrees outside versus cooling your house on a day when it's 100 degrees outside, right? In order to actually have the hot air leave your system, the coils have to reach a temperature that's greater than the air outside, right? And the rate at which the coils are going to be able to expel heat is going to be dependent upon that temperature difference. So if it's like 100 degrees outside, your air conditioner is going to have to run constantly, and the coils are probably only going to be slightly hotter than the outside air, so it's not going to get as cool as quickly, right? Does that make sense? So this depends on the external temperature. That means that your refrigerator works. I'm going to say some things that are going to be pretty obvious, but it's based on what we just said here. Your refrigerator is going to work a lot better if it's cold in your house. That's an obvious statement, right? Would you all agree with that? The refrigerator will work better when it's cold in your house? Yeah. That's really all that we're saying by this right here. That it depends on the external temperature. The air conditioner is going to work a lot better when it's cold outside. In fact, when it's cold enough outside, you don't need the air conditioner. Like today, probably, right? Today, you need a heater. So, there we go. Anyone have any questions? Refrigerators, heat engines in reverse. The same kind of idea, except instead of using heat to do work for you, you're using work to force air to go from a cold reservoir to a hot reservoir. You're forcing the air to do something it doesn't normally want to do. All right. So, this whole chapter that we've been discussing is about the second law of thermodynamics. And we haven't really stated what the second law is, but now we have some ability to state it with the second law of thermodynamics. There are going to be, I think, 3 or 4 ways that we're going to state what this is. They're all equivalent to each other, but they kind of just apply to different situations. Okay, first law of thermodynamics was, just to remind you, change in internal energy equal to Q minus W. That was the first law. Basically energy conservation, right? The second law is about what type of processes are possible in nature. All right. So, in general, we know that that it's impossible to make a heat engine that converts heat completely into work, the one that's 100% efficiency. So I'll put it like that. It's impossible to make a heat engine that converts 100% of the heat that comes in into work. It's basically a way to say that is that there's no perfectly efficient heat engine. And I could write this whole thing out here, but I think it would be just as viable to just to put the statement in the way that your book puts it, and then just talk about it, because I'd like to talk about what this means as opposed to spend time writing it, because it's a pretty long statement. So we're just going to copy the body of what they have here, and we're going to put that into the document. So this is the statement of the second law of thermodynamics. It states this. So it says, it's impossible for any system to undergo a process. This is any system. It's not just about heat engines. In which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work, with the system ending in the same state in which it began. So that is the second law of thermodynamics. I believe this is referred to as like the Planck-Maxwell version. Is that what they said? Kelvin-Planck statement, sorry. Or the engine statement. So let's just look at this and talk about what it means and why it's true. It's impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the complete heat completely into mechanical work. So why is this true, based on what we know so far? Why is this true? So we can go back to what I said at the beginning of class. If you have a body and it slides to rest, the organized motion of the body is converted into random motion of particles, right? When I have an object that's sliding on a surface, all the molecules of that object are moving with some velocity, and they come to rest. The tiny molecules shaking. Yeah, exactly. So you start off with an object that has all of the molecules kind of, on average, moving in one direction, and it turns that motion into a bunch of little tiny molecules that are vibrating. And again, since we can't actually control those individual molecules, it is effectively impossible to convert this motion completely back into work. We can convert part of it, though, right? So again, just to kind of state that, if I take, so body slides to rest, due to friction. We have organized motion that turns into random motion. And out of this random motion, which is molecules, it's impossible to convert that random motion completely back into mechanical work. We can convert part of it, though, in a heat engine. So that's what the heat engine does, right? It does as well as it can to... Apologize, I'm trying to get this to snap so I can get it to snap. That's not what I wanted to do. We'll just maximize it over here. Does this relate to turbulence? Is your question, Tom. I think that was the word for the gases moving randomly. Yeah, so turbulence was... So we talked about early on laminar flow and turbulent flow. And we said laminar flow was kind of the flow in pipes and the flow of... Well, if you have a stick of incense and you burn the incense or a match, the smoke that comes out of the end of it starts off traveling in a straight line. But then as the molecules start to move faster and faster and faster and they spread, the motion of the smoke that comes out of the incense stick starts to become really turbulent, right? Meaning that it's kind of tumbling all over the place and really random. So yeah, I mean, I think it has to be related to turbulence because turbulence is something that is difficult for us to describe because it involves random motion, and that random tumbling motion is due to temperature fluctuations and air currents and these kind of things. So yeah, I think it's similar to turbulence. If you think about it, like with turbulence, you're talking about the flow of a fluid and how we can't fully describe how that flow happens. And it's random for sure. So these are both random phenomena. And here what we're talking about is the random motion of the molecules of like the table and how we can't take that random motion and turn it into something usable for us, right? So in as much as we can't understand turbulence from a physical perspective and mathematical perspective, when we have a bunch of random motion, it's difficult to get that random motion and turn it into something that we can use, right? What's an example of motion that we can use? So if you think about a river in which all the water in the river is flowing in one direction, it's really easy to harness that energy, right? By constructing a water wheel and making it so that water wheel turns as the river flows by. And it's really easy to grab a lot of that energy. Now, even that water wheel, we're going to have problems that it's not going to be 100% efficient at converting the energy that comes in directly into mechanical work. And that's because the water wheel is going to have friction, right? And within that friction, you're going to have losses. At the end of the day, this really is exactly related to the idea that, when you're calculating, like in Physics 1A, when you're doing problems with energy, and you say that the work done by friction is equal to the change in energy of the system, right? It all kind of comes back to this idea right here, that work done by friction is not reversible, right? It's not something we can harness again to use for us. That's really what this is saying. And any process that has randomness to it is going to be like that. So that's what we call the second law of thermodynamics. It places a fundamental limit on the type of engines we can make. Another way to state this is just to say, I mean, you could take this entire thing right here, and knowing that we said earlier that E represented efficiency, you could just say that E is always less than 100%. With any real machine we make, the maximum efficiency that you could possibly get will always be less than 100%. That's really what it says. Efficiency is less than 100% with any machine we ever make. It is impossible to make a machine that is 100% efficient. It's a lot simpler to understand, right? For sure. A heat engine operating in cycle will never be 100% efficient. That's basically what that says. That's basically what it says. All right. You can state it in yet another way. There's kind of a refrigerator version of this. All right. So we'll call this second law of thermodynamics 1, second law of thermodynamics 2, double I, would be, it is impossible for any process to have as its sole result the transfer of heat from a cooler body to a hot body. This one is referred to as the refrigerator version. Or the Clausius statement. I don't know why it's important to name these things, but I guess it is. I feel like historically that the second law of thermodynamics was discovered by multiple people in different ways, and that might be why we have these different ideas like this. So this is the second statement. It means that it says the same thing technically. It just refers to a different process. So it says, it is impossible for any process to have as its sole result the transfer of heat from a cooler body to a hotter body. Its sole result. So why does the refrigerator not violate this version of the law? Yeah, because work is done, right? That's it. This one basically says, I mean, this is a complicated way of saying heat never flows from cold to hot. It's not that it never does, though, because we can make a refrigerator and we can force it to happen. It doesn't ever happen that way without work being put into the system, right? You can't have a refrigerator that works off of I don't know, just the atmosphere or something like that. You know, you can't have a refrigerator that's going to cool things off just automatically. There has to be some amount of heat input, some amount of work input, I should say. Okay, so there's the second law of thermodynamics. We're going to have another statement of it coming up. We won't get there today, but we'll talk about entropy next time. And when we talk about entropy, we'll have another statement of this, which says that entropy always increases in all thermodynamic processes. And ultimately, that's kind of the reason. It all comes down to this. Random as opposed to causal, you know? If you have motion that functions off of cause and effect, you can extract energy from it very easily, right? Water falls from the top of a waterfall down to the bottom. You can take that flow of water, that is, its flow is caused by gravity, and you can extract energy from it very, very easily, right? Water flowing in a river, wind flowing across open plains can be converted into energy very easily via wind turbines, right? But when the motion is random, you just can't do much with it, you know? Imagine trying to have a wind farm where you're trying to extract energy from wind, And imagine that the air that's nearby never flows in one direction. Does that make sense? So you have windmills, but the air is flowing left and right and left and right and up and down. It's going to be very difficult to extract energy from that, right? Same thing would be true if you're out sailing on the ocean, right? You can sail on the ocean as long as you have wind that blows really in any direction. If you have stale air, where the air is just not flowing at all, you're not going to be able to move your sails, right? If you have wind that flows in any one direction, though, you can orient your sail to get energy from it, right? But if the wind blows left and then right and then left and then right, you're going to have a lot of hard time getting any. You're going to have a very difficult time getting any energy out of that. So it's the fact that the motion of molecules is random, and that it's difficult to extract energy from things that move randomly. Not impossible, it's just difficult. And it's difficult enough that it's never going to be 100% efficient, because it just isn't. Because it's random. Random means unpredictable, right? It means in a way such that we can't gain anything from it, you know? It's like, I don't know. I think I've given enough kind of analogies here, but I was going to say it's like looking at code that's been, not code, like it's like looking at, trying to read a message that's been, what's the word for it? What's it called in cryptography when you scramble a message? Just encoded, I guess. If you have a message that's been, what word am I looking for here? If I send you a message, I want to make sure nobody else can read it unless they have a key. What do you call that? Those of you that are familiar with encrypted. Yeah, encrypted is the word I'm looking for, yeah. So encoded or encrypted, right? So if you have a message that's been encrypted, it's just a bunch of random symbols. And getting any information out of that's going to be very difficult unless you have the key that inputs into it, right? It's the same thing. Random information and random motion are very similar in that sense. So a lot of the things we're going to discuss, not only do they apply to the flow of heat and work, but they also apply to the flow of information, right? So, all right. We have a little bit of time left. I'm just going to start talking about the Carnot cycle. I don't think it's realistic that we're going to get through much of this, but I'm just going to mention some things here. So the Carnot cycle, the idea was, someone was like, I know that the second law of thermodynamics is true, right? But what if we could design a process, okay? This is really fascinating, what we're going to talk about here. The idea would be, suppose that we design a process, right, where we avoid all these problems, right? We avoid these issues that the second law of thermodynamics says. It says it's impossible, but what do we mean by impossible? Is it impossible like it would have been impossible for cavemen to go to the moon, whereas with better technology, we're able to now travel to the moon, right? Or is it impossible like it's fundamentally impossible? That's really the question. Is it impossible such that someday we will overcome this? Or is it actually impossible, okay? And so the Carnot cycle attempts to kind of figure this out. So this is a hypothetical process. It's purely for, yeah, I kind of figured out that that's what you meant, Daniel. Yeah, that you were talking about is like, is it really impossible, or is it? All I can say is like, unless we come up with some new physics, is the idea. We would need new physics. We would need to find something new. We may find something new soon though. It's hypothetical and ideal, okay? And basically the idea is this: we saw above that it's irreversible randomness that is the problem, right? So what if we could make a process that avoids all of these random things? Yeah, we avoid all the irreversible processes, right? So for maximum efficiency, we basically have to avoid irreversible processes. What that means is that every process has to be either isothermal or adiabatic. They either have to occur at constant temperature, because its temperature changes are where you increase randomness, all right? Or adiabatic, which means there's no heat flowing in and out of the system. Now, adiabatic by itself is already very idealized, right? We said earlier that one of the reasons why, we calculated the efficiency of an automobile engine and we said the answer was 56%, but then I said in reality it's actually 35%, it's 20% less efficient than you think, and the main reason is because of friction. Adiabatic implies that you can construct a process that has no friction. That's just utterly unrealistic, right? But it doesn't matter, because even with, just as a preview to where we're going here, even with these assumptions, there's still going to be an upper limit to the efficiency of an engine. That's what's amazing about this, is that even when you get rid of all of the irreversible processes, there's still going to be an upper limit to the efficiency. And that's where, to answer your question more seriously, Daniel, I do believe that the second law is true in the sense that it is actually impossible. It is fundamentally impossible at a molecular level to overcome the second law of thermodynamics, unfortunately. I say unfortunately because otherwise we could make engines that were perfectly efficient, and that once you start them moving, that So here's the Carnot cycle. I really don't know if I like. I don't know if I like the picture in this book. We're gonna use it though because it's the textbook y'all have. But this is an example of the Carnot cycle, and I'm gonna kind of write down what the steps are here to the right. Okay, we're gonna start from 1, then go to 2, then go to 3, and then go to 4, and everything is said within this diagram here. And I'll make it just a little bit bigger so y'all can see it better. Okay, so process 1, isothermal expansion. So we have a gas. It has heat that comes in here, okay? And the heat that comes in, QH, is greater than 0. The work done is greater than 0. So basically you have an enclosed gas. Heat comes in, and it expands, okay? So gas expands isothermally at TH, okay? I'll just write isothermal expansion. So the idea here would have to be that the way I think about it is you place your system onto a hot plate or something like that, right? So I thought I clicked the red one. Come on, let me click this. Well, it's not working. The idea would be that you'd have some kind of hot plate down here, right? And you'd put your gas onto that hot plate, and somehow the gas doesn't heat up. It doesn't change temperature, but it does expand, okay? So temperature stays constant, okay? And where are we on this one? So these are isotherms. Each of these blue lines is an isotherm. TH is A to B, so we're going from A to B. We're coming along this isotherm right here, from A to B. Okay. Now we're going to go from B to C, so we're actually going to go to a colder temperature. And this is going to be adiabatic expansion. Do I even need to write all these steps down? Well, this is A to B. I'll write down what I wrote down in this case. Gas expands adiabatically until the temperature drops to CC. So already here, adiabatic it should throw off alarm bells in your head that this is impossible, but that's okay. Gas expands adiabatically until the temperature goes to TC. So we have a new temperature down here, TC. We're on this isotherm now. Okay. You'll notice that the sliver inside of here, where the work is done, is really tiny. Okay, and then part 3. So how would this happen? So I guess then this is isothermal expansion, but then I guess you remove it from the heat reservoir. This is the part that's kind of confusing to me here, but there's another textbook that I think does a little better job of this. I guess it continues to expand. Why does it continue to expand? I understand how Q is equal to 0. I don't fully understand the process from 1 to 2. So you start off and there's some heat here, right, that's coming in. And you allow the system... Wow, this really sucks because I can't switch pens now. I don't know why it does this sometimes. Oop, did I do it? I fixed it somehow. Is it because my palm's on this? Something's happening. Something is like getting stuck down or something that it's doing this. There it goes. Okay. Do y'all understand this process? It says isothermal expansion at TH. I get that. You put heat in, it expands, right? Why would it continue to expand after you remove the heat? What do you think?
So heat. Wait, okay, so the temperature is the same, A to B,
Yep.
and
Yeah,
then you let it
I think Kenny's
expand.
right. Residual energy left within the molecules allow it to just keep expanding. That's probably right. So probably like the heat comes in and it expands some, but then you just abruptly remove the heat source, so it kind of continues to expand because it's going to have to cool off. What's it going to do? Is it going to expand until, like, is it insulated from its environment? I think it would have to be. If it's adiabatic expansion, it has to be insulated, right? All right, well, somehow the gas continues to expand. I think Kenny's probably right. Probably some residual energy left within the molecules, but it cools down in that process. All right, so it's expanding here, but the temperature is not changing, and here it's expanding, but the temperature is dropping because you removed your heat source. All right, and again, there's work done. This is positive work, positive work. All right, next you take the same system and you put it in contact with a cold reservoir. All right, so from C to D, what you get is isothermal compression. So you give it some cold reservoir that can absorb an infinite amount of heat, and you allow it to, and it just needs to be colder than this object, except it's isothermal compression, right? So it's going to, the gas is going to compress, which means it's going to do negative work, but it's doing so as it's in contact. Basically, this is so weird. This part is so weird too, because it's like if you place it in contact with a cold reservoir, you'd think that the temperature would drop, but the idea here is that instead of the temperature dropping, it's just the volume of the container that's changing, basically, but the temperature is remaining constant from C to D. And then finally, you remove the system, and due to the fact that its temperature is less, it continues to compress. And then you put it back on the hot reservoir. So really, all that you're doing here is you're taking a system, you're putting it on a hot reservoir, you're taking it off, letting it expand, then you put it on a cold reservoir, you take it off, and you let it compress. That's it. That's the Carnot cycle. Take your system, put it on a hot object, take it off, put it on a cold object, take it off, and then repeat. And maybe you do this via a temperature source here where you can turn it on and off quickly, like a flame or something like this. That's it. Short engine of nature, the mechanical universe. Yeah, Baron, I agree. This diagram is really confusing. So the other version of this diagram, do I have it still pulled up here? I'm just going to pull it up, and we can just talk about it. Is this one, right? Yeah, I like this picture better. Oops. You can actually see, yeah, see, this is the piece that's missing. This is the one I was wondering about. Like, is it insulated? Okay. Yeah, this is the key, is that it's insulated. It's the exact same process. Energy reservoir at TH, right? Comes in, isothermal expansion. You thermally insulate it, so now no temperature can come in, but then it kind of keeps going. And then you take it, you drop it on here so it's cool, and it undergoes isothermal compression. It's isothermal because it's in contact with the reservoir, right? And the fact that it's touching the reservoir means that the temperature can't really change. I mean, the idea here is that it's isothermal, though, right? So whatever the temperature is in this picture, it's also the same as the temperature in this picture, right? And then you thermally insulate it, and then you go back again. So that's the idea. So that's the Carnot cycle. And what we'll derive next time is the efficiency of the Carnot engine. And what we're going to find out is that even this engine is going to have not 100% efficiency. So that's kind of what we want to start next class off with, and then we'll go into talking about entropy. We'll talk about microstates and macrostates, what entropy is, and then I guess if we have time after all that, we'll talk about waves, sound waves and stuff. So we'll be done with thermodynamics next time, and we'll have the rest of the semester to talk about waves, which will be quite a bit of time, actually. All right, so I'm stopping right there. If you guys have any questions, let me know.